Continuing on with week 12, exam 3 preparation. This is a seismic instrument. This is also a problem, by the way, from Miriam and Craig. It's a dynamics book, not a vibration book. So they might have different things from R and different nomenclature and whatever. So we could see that it has a vertical vibration frequency of 5 hertz. All right, so it's the FF is 5 hertz. And a double amplitude, I don't know why we need to call it double amplitudes, of 18 millimeters, right? So that's the amount that this thing is going up is, let's say that 2 times our Y is equal to 18 millimeters. Therefore, one of our Y's is equal to, but that's fine for us. The sensing element has a mass of 2 kilograms and a spring stiffness of 1.5 or 1,500 newtons per meter. The comma will kind of ugly. Not any better. All right. And the motion of the mass relative to the instrument, right? That's part of the base. Relative to the instrument base is recorded on a revolving drum. This guy right here. And with a double amplitude, once again, so that's going to be 2 times Z, because that's the relative motion there, 24 millimeters. Again, the steady state, I'm going to calculate the viscous damping C. All right, so let's approach this. First off, let me get the forcing frequency into radians per second. So that's going to be 31.42. You could do that in your heads, right? Just 10 times pi. We get the natural frequency, square root of K over M, or the square root of 1,500 stiffness, and the mass of it is 2. So we have ourselves 27.39 radians per second. So our R is omega F over omega N, 31.42 divided by 27.39. We can expect close to 1, and we got it. And then we have some math to take care of here. So we have our main equation for this. This is a vibrometer type of deal. It's going to be R squared over square root of 1 minus R squared squared plus 2 squiggle R squared. So we can find the Z over Z, Z over Y. It's going to be 24 over 18. The half cycle thing is going to cancel out. 1.333. And that's going to equal 1.4147. Sorry about that. I messed that up. Square root of 1 minus 1.147 squared plus 2 squiggle times 1. I keep forgetting that 147 whole thing squared. You can see that we have to do a little bit of manipulation out here. Not too terribly bad. First, I would bring this over to the right-hand side. I would divide through this one by that one, and then square it, and then subtract out the 1 minus this value right here, until we're left with this right here, and you can have a squiggle squared and divide out the other peeps. And the last thing, so what you end up getting is about 0.4078 from that. It's a little bit of a tedious calculation. It's not there's a lot of room for mistakes, at least a lot of keystrokes on the calculator. We can get the critical, could have got that always already. Mass is 2 kilograms. The natural frequency was 27.39. So we have a 109.6 Newton seconds per meter. So we're able to find the damping coefficient by taking the damping ratio and multiplying it by that critical. And so we get a C is equal to 44.67 Newton seconds per meter. And isn't it satisfying when you get this the correct answer? Hopefully. I used to do that all the time with all of my answers. I always made them kind of like this little backlit kind of shadow thing. That's amazing. All right. 6 minute and change problem. Not a bad choice.